Good morning students. In today's class, we will discuss about unsymmetrical fault analysis on power system. So we know what are the unsymmetrical faults. LG fault, LL fault, LLG fault. So till now, in the previous lectures, we have discussed about the unsymmetrical fault analysis on an unloaded generator with and without fault impedance. So from today's class, we are going to discuss about the unsymmetrical fault analysis on a power system network. So it may have one or more power system components like generator, transformers, transmission lines, motor loads, etc. Okay. So for the given power system network, we have to find out the fault current. So the unsymmetrical fault analysis on the given power system network is analyzed using Thevenin's equivalent network of the positive, negative and zero sequence networks. Okay. So given any power system network, we have to draw the positive sequence network, negative sequence network and zero sequence network separately for the given power system network. So once we draw these three networks separately, we have to find the equivalent network. Okay. So the Thevenin's equivalent network will comprise of a voltage source and one equivalent impedance in the positive sequence network and negative sequence equivalent impedance and zero sequence impedance. Understood? So for the given power system network, we have to draw the positive sequence network, negative sequence network, zero sequence network separately. So after drawing these three sequence networks separately, draw the Thevenin's equivalent positive sequence network, Thevenin's equivalent negative sequence network, Thevenin's equivalent zero sequence network. Okay. And in the Thevenin's equivalent positive sequence network, it consists of one voltage called as pre-fault voltage VPF and one positive Thevenin equivalent impedance. In the case of Thevenin equivalent negative sequence network, it has only Thevenin's equivalent negative impedance. In zero sequence Thevenin's equivalent network, it will have only Thevenin equivalent zero sequence impedance. Okay. So this Thevenin's equivalent impedances are calculated with respect to the fault point and the reference. Okay. So the Thevenin's equivalent impedances and the Thevenin's equivalent circuit are obtained with respect to fault point and the reference. So I told about the pre-fault voltage. Okay. So pre-fault voltage is the voltage before the occurrence of the fault. So before the occurrence of the fault, the system will be in balanced condition. So the pre-fault voltages and currents are balanced. Okay. So the pre-fault voltages and currents are balanced. So hence the pre-fault voltage at the fault point is a balanced voltage and it will have only positive sequence component. Okay, so this concept we have discussed in the earlier classes. So the pre-fault voltage at the fault point is a balanced voltage and it can have only the positive sequence component. Okay, so we are coming again to the same point. So this pre-fault voltage source, pre-fault voltage at the fault point should appear only in the positive sequence equivalent network. Okay. So in the negative and zero sequence network, there will not be any pre-fault voltage, or we can say the negative and zero sequence component of the pre-fault voltage will be zero at the fault point. Okay. Yeah. The pre-fault voltage at the fault point can also be called as the Thevenin's voltage of the positive sequence network. So now we are going to draw the Thevenin's equivalent positive, negative and zero sequence network. So for that, let us consider Z1 as the Thevenin's impedance of positive sequence network, Z2 as the Thevenin's impedance of negative sequence network, Z0 as the Thevenin's impedance of zero sequence network. And Vpf is the pre-fault voltage at the fault point. So these three networks or the circuits represent the Thevenin equivalent network of positive, negative and zero sequence networks. Okay. So positive equivalent, Thevenin's equivalent of positive network will have Vpf and the Thevenin's equivalent impedance, whereas negative sequence, equivalent negative sequence network will have only the Thevenin's negative sequence impedance, and the equivalent zero sequence network will have only Thevenin's equivalent of the zero sequence impedance. Okay. So we draw the three sequence networks of the given power system separately. Okay. Then we combine the three sequence networks for LL, LG and LLG. We know in the case of LG, all the three sequence networks will be in series. Okay. In the case of LG, all the three sequence networks will be in series. In the case of LL, positive and negative will be in parallel, whereas zero sequence network will not come into the combined network. In the case of LLG fault, all the three sequence networks will be in parallel. Okay. So as a summary, in the case of an unsymmetrical fault analysis of the given power system network, first you have to, step 1 is to draw the positive, negative and zero sequence networks of the given power system network separately. Okay. So the given power system network will be having generators, transmission lines, transformers as well as some kind of loads. Okay. So your positive, negative and zero sequence network will be having some impedances. Okay. And the fault point will be mentioned in the given power system network. Okay. So after step 1, step 2 is to draw the Thevenin's equivalent positive, negative and zero sequence network. So the Thevenin equivalent positive sequence network will have Vpf in series with positive sequence Thevenin impedance, whereas negative and zero sequence network, equivalent network, Thevenin equivalent network will have only the negative Thevenin impedance and zero Thevenin impedance respectively. Okay. So after drawing, step 2 is to draw the Thevenin's equivalent of positive, negative and zero. So step 3 will be, depending upon the type of fault, these three equivalent networks you have to combine. Okay. If it is LG, all three should be in series. If it is LL, a positive and negative should be in parallel. If it is LLG, all the three should be in parallel. Okay. So these are all known equations. Yeah. Then let us go into the derivation of the three types of faults, that is LG, LL and LLG on a power system. Okay. So till now the first 6 derivations whatever we have seen are LG, LL, LLG fault on an unloaded generator with and without fault impedance. So these derivations are for the three types of faults on a general power system with and without fault impedance. Okay. So what I have done, I have written only the important results, important formulae. I have not done the derivation. So you have to include the derivation and complete it. Okay. So first coming to LG fault on a power system. So coming to a general power system, don't draw the circuit of a generator. You represent the power system by 3 transmission lines. That's enough. Okay. So this is the circuit diagram for a general power system. So we assume single line to ground fault occurs on phase A. So the fault current IF is equal to IA. Again we are writing for unloaded condition. These are the initial terminal conditions. Okay. IB, IC is equal to 0 and VA is equal to 0. And IA0, IA1, IA2 is equal to IA by 3, which will give you IA is equal to 3IA1. and IA1 is equal to VPF by Z1 plus Z2 plus Z0. Okay, and IF is IA, which is 3 IA1. And for LG fault on a power system without fault impedance, we connect all the 3 sequence networks in series. Okay, and the 3 major changes you have to do for a general power system is represent the circuit by 3 lines by transmission line network. Okay, second one is you replace EA by VPF, because EA is the induced EMF per phase of generator. So this is a general derivation, so don't write EA. Okay, VPF, replace EA by VPF. So VPF is the pre-fault voltage at the fault point for the given power system network. Okay, then we don't include that Z10 also. Here we don't include Z10. Okay, so Z10 is specifically for a generator whose neutral is grounded through a neutral impedance Z10. So here it is not specific to generator, so please don't include this Z10 here. Okay, so I have not done the derivation. You write the derivation and complete it. Then coming to LG fault through fault impedance, we include this ZF. Okay, so line A to ground fault through a fault impedance ZF, and these are the important relations we got from the derivation, and this is the combined network, 3 networks in series through 3 ZF. Okay, derivation same as generator, replace EA by VPF. In the same way, I have compared the LL fault on a power system with and without fault impedance. Okay, so LL fault between lines B and C, this is without fault impedance. Here it is through fault impedance. Okay, and the important relations I have written, and the 3 changes what we have to do is, for a general power system, represent the 3 lines. Okay, then EA replaced by pre-fault voltage VPF at the fault point. Then don't draw the reactance. You can put this Z1 impedance symbol. Okay, just represent by a small rectangle. Okay, then the third type of fault is LLG fault, with and without fault impedance. So the double line with respect to ground, line B and C are shorted, connected to ground. Through fault impedance means B and C shorted, and the fault impedance will be there between the shorted terminals as well as the ground. Okay, so the relations whatever I have written here are from the previous derivation. Only thing is I have replaced EA by VPF in both the derivations. You can refer the previous derivations and complete it. I have drawn only the combined network. Okay, so I have written everywhere like derivation same as generator. So you have to copy down those derivations.